Okay, today we're starting section 3. This is the third of 5 sections. We call these thermochemical equations. Guys, in unit 8, right before you would have taken your semester exam, you did unit 8, which was chemical equations. Well, these are thermochemical equations. They are no different except for you're actually considering heat now, either heat lost or heat gained. Let's make something very clear here. There are two types of energy transfers. The first is exothermic. Does this mean energy is gained or energy is lost? Energy is lost. Thank you for participating. So if you're actually looking at a thermochemical equation, would the energy be considered a reactant or would it be considered a product? Yeah, joules or kilojoules are a product. In an exothermic reaction, listen carefully. I know that you all are visual learners, but I want to see if you can pick up on what I'm saying. In an exothermic reaction, do you have more energy at the beginning or at the end of the reaction? Yeah, at the beginning. And so I'll visualize all this for you. So first off, here is an actual thermochemical equation that represents an energy loss. We did this one last class. All right. As you all know by now, these are the reactants. These are the products. And the fact that I see energy as a product, this indicates that energy was lost. Another way that we could write this, everyone, is like this. So this is the chemical reaction, and then this is telling you what happened with the energy. Why is the 1625 kilojoules a negative value here, Emma? Energy lost it. You know, I was going over my personal bank account yesterday. I'm looking at expenditures, seeing how much money I've been spending. Every time everything's money lost, it says like negative 20 bucks, negative $25. It's lost. It's gone. That would be a product. All right. If you actually look at this on a chemical reaction, as a reaction, remember that the x-axis is the progress of the reaction. The y-axis is your actual energy level. It looks like this. These are your reactants. These are your products. You lost energy. That's all indicative of an exothermic reaction. Are there any questions when it comes to exothermic reactions? Okay, what's the opposite of exothermic? Endothermic. What does endo mean? You gain. It goes inside. We get our word enter from this prefix. And all of you are mammals. You have an endoskeleton. It's inside. So this is where you have an energy gain. Is energy going to be a reactant or a product? Joules or kilojoules are a reactant. Good. Oops. All right, so here is a chemical equation we did yesterday. Where would I put the kilojoules? Would I put kilojoules as a reactant or as a product? Reactant. Right, so I could put them right here. So here's my reactants. Here's my products. The fact that kilojoules is a reactant indicates that this is an endothermic reaction. Another way I could write this equation is like this. What would delta H be? Positive or negative 27? You don't necessarily have to write positive. I know that you guys don't say, I have positive $20. No one says it like that. If you just put 27 kilojoules, that's fine. But I just want to make sure I'm definitely getting the message across that this is 27 kilojoules gained. Okay? If you actually looked at it on an XY axis, it will look like this. These are your product, or excuse me, whoa. These are your reactants. These are your products. And that is going to be an endothermic reaction. Yeah. Or from another substance. Okay. Let's get to another vocab term, shall we? We're going to talk about different types of chemical reactions. Just when we did Unit 8, you learned that there were synthesis reactions, decomposition reactions, single replacement, double replacement, and combustion. Well, there's different types of thermochemical equations too. And the first one is going to be combustion, what we actually call the enthalpy of combustion. The symbol is going to be delta H with the subscript COMB. What do you think COMB stands for? It just stands for combustion. That's right. Enthalpy of combustion is one of your terms. All right. Next is this symbol, delta H naught. Now that is a zero, but another way to say zero is not. You know, when I was a freshman in college or high school, when I was a freshman in high school, yeah, the year 2000 happened, and you could say it was the year 2000, 2000. You could also say two not. You know, if we're currently in the year 2021, we could say 2021 or 2021. So not just means zero. We call this delta H with a zero superscript. This stands for standard enthalpy. The zero superscript, remember a subscript is on the bottom. A superscript is like an exponent. Super means above, sub means below. The zero superscript tells you that the enthalpy changes were determined with all reactants and products. Here's a new term, guys. At standard conditions. This is not the same as standard temperature and pressure. Standard conditions means 1 atmosphere and 25 degrees Celsius, which is 298 Kelvin. Do not get this confused with STP. Standard temperature and pressure is 1 atmosphere at 0 degrees Celsius. This is not STP. So I'm going to make that very clear. Not STP. Standard temperature is 0 degrees Celsius. This is 25 degrees Celsius. Big difference. All right, so I want to give you an example of an actual combustion reaction, and it is something that you all are probably doing right now inside your own bodies. I know that some of you have some biology knowledge lurking in your brain. What is that process that takes place in your mitochondria that produces ATP? There it is, cellular respiration. The chemical equation for cellular respiration is 1 molecule of glucose, C6H12O6, reacts with 6 molecules of oxygen, O2, to yield 6 molecules of CO2 and 6 molecules of H2O. The change in the enthalpy of combustion is negative 2,808 kilojoules. So by burning sugar, which is what cell respiration is all about. I know that I'm getting into the biology aspect of it. But by burning sugar, or I guess you could say by combusting it, you are producing that much energy. 2,808 kilojoules worth. Because that is energy being released. So it's gone. Right. So if I actually drew this as, oops, where'd it go? There we go. If I drew this as a graph, it will look like this. You ready? Check this out. That's obviously exothermic. Here is C6H12O6 plus 6O2. Down here, we're going to say 6 CO2 plus 6 H2O. What is that right there? That red line I drew. Well, what does it represent first, before you tell me exactly what it is? That's the change in energy. That is the change of energy. The amount of energy that you have from the reactants down to the products, it's like, here's where I am. Here's where I started. Here's how it's going. I started here. Now I'm down here. What's the difference? At the beginning of the school year, Emma had $5. Now she has 500. It went from here to here. What's the difference? Positive $495. Well, if I started here at the reactant level and I ended down here at the product level, that's clearly an energy loss, but that is your change in enthalpy. This is a combustion reaction, so you would say this is your change in the enthalpy of combustion, and that would be negative 2808 kilojoules. Why is it negative? Because it's being lost. What I would like to do now is I just want to show you guys and make you aware of this in case you have to see it on your unit review. I want to show you a slide from your PowerPoint. This is a chart that shows the standard enthalpies of combustion. There may be homework problems that ask you to refer to this table. This table is found in your textbook, but it is also found on your PowerPoint, which you can access on Canvas. It shows you the enthalpies of combustion for table sugar, octane, glucose, propane, and methane. You can see that what do they all have in common? So are those energy losses or energy gains? You want to know something that's pretty unique? I'm sure that in a few weeks, some of you might be having a little barbecue for Memorial Day weekend or 4th of July weekend in a couple months. You use a propane tank for that. I want you to look at how much energy is burned on 1 molecule of propane. Compare that to the amount of energy burned from table sugar that you eat. Your body produces more energy from just burning sugar than the energy that is produced from a propane grill. You are little furnaces. You're mammals. You have to generate your own heat. The amount of energy the human body produces is astonishing, and we don't even realize it. You are perpetual furnaces for your whole life. You have to keep that fire burning. That's what eating is all about. Even octane, stuff you put in your car, doesn't burn as much energy as your own cells do when breaking down sugar. That's crazy. All right, let's go back. I will refer back to that PowerPoint a little bit later, okay? Next, I'd like to talk about changes of state. I mean state of matter. Now, I want to make sure that we're all very clear on something. What is it called when you go from a solid to a liquid? What is this known as? This is known as melting. I'm going to give you a new name, okay? This is the same thing as melting. Just like Derek is another name for the coolest kid at playing high school. Same thing. Right. Yeah. No disagreements here. Fusion. Melting is also going to be called fusion today. And what do you call liquid to gas? Not evaporation, vaporization. Just vaporization.
My bad. No, he called me cool and it went to my head.
Well, you know, the first part of a problem is admitting that you have one. Good job. All right. Now, I use red. Red is a warm color. If you watch a weather map, they indicate hot temps with red. So do you think going from a solid to a liquid to a gas is a endothermic process or an exothermic process? Endo. This is a heating up process. These are all endothermic. No. Liquid to gas doesn't have a different name. It does not. All right. Well, let's circle back and go in the reverse direction. What do we call a gas to a liquid? What is this known as? Condensation. What do we call liquid to solid? Freezing is one word. I'm going to teach you another one. Freezing is one. The other one, everybody, is going to be solidification. Should make sense, right? Something that's getting solid is solidifying. Fusion, yeah, it's can be referred to something totally different. All right, now sometimes this is really hard for your brains to wrap around. I remember the day that Mr. Bush was sitting in class and Jade was sitting right there, and I kept going back and forth with her, and he was laughing just because she was like, "I don't get it, I don't get it," and I did not let her off the hook, and she eventually got it. This is going back to that lesson, okay? So some of you might be feeling how she did that day. What temperature does liquid water freeze into ice? 0 degrees Celsius. At what temperature does ice melt into liquid water?
0 degrees Celsius.
Right. When you come into my classroom, what does that door serve as? When you leave my classroom, what does that same door serve as? The same temperature can mean two different things. Just depends if you're coming or if you're going. So check this out. Let's put it on the board. We have we have 0 degrees Celsius. We have 100 degrees Celsius. I'm going to work with water here, okay? When I go from here, ready? That X, am I above or below 0? I'm below 0. So what state of water am I? Solid, ice, same thing. When I go from here, right there, what just happened? I melted. I went above 0, did I not? I crossed that threshold. I fused, I melted, same thing. Let's keep it going. Let's say I go, I'm up here now. I vaporize, so what state am I in?
Yes.
All right, now watch this. Let's say I'm here. Let's use a different color. John Dennis, I want to hear from you. I'm here. What state of water am I currently right now? Ice, liquid, or gas? Gas. What happens when this happens? Boop, 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 boop. What state am I in now? Good. And let's say I go from here. Boop, 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 boop. What state am I now? Solid. What happened? Solidification or freezing. Emma, at what temperature did water go from solid to liquid?
0 degrees.
It happened at 0 degrees Celsius. Booyah, right there. At what temperature, Emma, did liquid become solid? Same one. That is sometimes very hard for people to, their brain's like, frozen. It's just this, it's the same door. It just depends on if you're using it as an entrance or an exit. The door swings both ways. Same here. At 100 degrees Celsius, liquid becomes gas. Or at least, let me rephrase that. Water becomes gas. Everything has different boiling points and freezing points and all that. And then at 100 degrees Celsius, gas will condense into a liquid. It just depends if you're heating up or if you're cooling down. That's all. That's all it depends on. So I'm not totally convinced you guys get that, but you can prove it to me as we move on. Here's your next vocab term. We have been getting a lot of these today, or this week. Enthalpy of fusion. The symbol for enthalpy of fusion is delta H with a subscript F, U, S. The definition is the amount of heat required to melt, there's that word, melt, 1 mole of a solid substance. Remember, another word for melting in this unit is going to be fusion. And then we also have enthalpy of vaporization. The symbol is going to be delta H, V, A, P. What do you think the definition is based on the definition of the enthalpy of fusion? Yeah. The amount of heat required to vaporize 1 mole of a liquid substance. What do both of these processes have in common? Psst, psst, psst. I use the color red. They're endothermic, which means they absorb heat. So what will their values always be? Positive or negative? They're always going to have positive values.
What? Oh, true.
Okay, I have a chart here for you. This is where I hope you are going to have your mind blown, okay? Let's go to a few pages. There it is. All right. These are standard enthalpies of fusion, everybody. Now, let's see if we can really grasp this. There's only 5 students in class. Most students are taking an exam today. So you guys are going to be speaking for everybody. I want you to prove to everyone else that this can happen. Emma, how many kilojoules per mole will liquid water become a gas?
Is this on the chart?
Yeah, it's on the chart.
let me scoot.
Scoot over. She's going to scoot up so she can see better.
40.7?
40.7 kilojoules per mole. Now, Derek, if it takes 40.7 kilojoules per mole to go from liquid, bloop, 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 to gas for water, how many kilojoules per mole are lost when you go from gas to liquid water? Bloop, bloop, bloop.
40.7.
Is that positive or negative?
Negative.
Here's the breakthrough, everybody. You listening? You listening? You listening? You listening? This chart shows what we can see with our own eyes, vaporization and fusion. If you put a negative in front of every single number, what do those numbers represent now?
Condensation and solidification.
Condensation and solidification. You are going to see this on your homework, guaranteed. And on next Thursday, we're working on this. I don't want to hear any of you five say, Mr. Thorson, this problem is asking me for the enthalpy heat of condensation and I can't find it. There's no chart that says condensation. And then I'm going to say, turn to this page, find this chart. What substance are you looking for? The condensation of water. Okay. What do you see in this chart? You see vaporization. All right. Vaporization is from what to what? Liquid to gas. Okay. So what's the opposite of vaporization? Condensation. Oh. So it's the opposite of the number. Yeah. Negative 40.7. Got it? What's that, Derek?
I said I'm loving the monologue.
That's how it's going to go. You know it. I've seen it. I've lived it. So, Derek,
Yes.
how many kilojoules per mole will it take for ammonia to freeze or solidify?
5.66.
Ah.
No. Negative.
Negative 5.66.
Yes, but when you write it in the equation, it doesn't show up as negative. It's just 5.66.
Negative 5.66. Yes, Arshawn.
Is there like a delta H, like con or solid, or do
Yep.
you miss it?
You have to do, that's exactly what I put, con for condensation, cond for condensation, and solid for solidification. Yeah, that's it.
And then those always be negative.
Yep, they're always going to be negative, so let's do that. Let's see if you guys have that. Nope, those are not vocab terms, but it is important to know. Enthalpy, heat of condensation is going to be delta H subscript COND, close parenthesis. And then the other one is going to be enthalpy heat of solidification.
Why is it enthalpy heat? I thought enthalpy already said heat.
Oh, did I say something different? I guess, yeah, that was just a force of habit. You don't have to put enthalpy or heat in there. This is going to be delta H subscript SOLID. Now, I use blue. It's a cool color. What do you think that means? What? They're both exothermic, which means that the delta H is always going to be a negative value. Now, let's make something very clear here. This is the opposite of the enthalpy of vaporization, and this is the opposite of enthalpy change of fusion. So fusion is like positive 40.7, solidification is going to be negative 40.7. If vaporization is 23.4, then condensation is going to be negative 23.4. So let's go back up here. I want to show you guys some numbers. To go from solid to liquid, this was enthalpy change, or excuse me, enthalpy of what? Fusion. What's the value for water? Well, you don't have that at your disposal, so I'll tell you. 6.01 kilojoules per mole. That's on the chart, but I know you can't see your chart right now. 6.01 kilojoules per mole. Let's go up here. Enthalpy change of, enthalpy of vaporization is going to be 40.7. This is for water, everybody. Every substance is different. So knowing that, Derek, if it took 40.7 kilojoules per mole to turn liquid water into water vapor, what's it going to be for the enthalpy of condensation? Negative 40.7 kilojoules per mole would be correct. And Kayla, if it took 6.01 kilojoules per mole to go from solid to liquid, what will it be to go from liquid to solid? That's right. I expect you guys to help your classmates if they don't watch this video, which they should, next Thursday. All right, so let's do a problem. Here we go. This is example problem number 4. What?
If we had like problems that needed enthalpy, would we be given that chart?
Yeah.
So we wouldn't have to memorize them, right?
No, I'm not going to make you memorize them. I'm not that mean. All right. So I will walk you through this. I'll let you catch up. We need to first identify our knowns and our unknowns, what we are being given and what we are being asked to find or solve. So, Derek, can you read the problem and tell me what a known value is?
54 grams glucose.
And it says glucose is C6H12O6. Emma, can you read what we're being asked to find? Can you see that from there?
Yeah. How much heat is it being?
Evolved. Evolved means produced, like made.
Oh, evolved. When 54 grams of glucose is done?
Yeah. How much heat, and what is heat measured in? I mean, we're going to say actually kilojoules on this one. If you said joules, you'll find out later it would be kilojoules. Okay, so we're trying to find kilojoules. We need to figure out how many kilojoules are produced when you burn that much sugar. So this is where you would have to look at the chart. Now, would you want to look at the vaporization chart, the solidification chart, or the combustion chart? You want to look at the combustion chart. What substance are you going to look for? You want to look for glucose, so I'll provide that for you, as promised. Is that the combustion chart? No. Is that the combustion chart?
Yes.
And what substance are you looking for? Glucose looks to be the middle. So what is the enthalpy of combustion for glucose? Negative 2808. That is where we are getting that number from. Understand? We're not making it up. Dare to not just imagine it. The change in enthalpy of combustion is 2808 kilojoules per mole. Everybody, this right here is going to be a conversion factor. What two units of measurement can you convert between? And? Kilojoules. You can go back and forth between moles and kilojoules and kilojoules and moles. I want you to look at the sugar we have. Is that measured in moles? It's not measured in moles. It's measured in grams. Have you ever used a conversion in this classroom? You could go from grams to moles. It's called molar mass. Can you calculate the molar mass of glucose so that we can convert the glucose into kilojoules? So the first thing I need you to find, step one, find the molar mass of C6H12O6. Nobody shout it out. There's some people in here that totally forgot. I can feel it. Well, I would suggest you memorize it, but I haven't memorized. But if you didn't memorize it, you all know how to find it. What is the molar mass of one carbon? 12 grams per mole. How many carbons are there? What is 12 times 6? 72 grams per mole. What is the molar mass of hydrogen? 1. How many hydrogens are there? So it's going to be 12.0 grams per mole. What is the molar mass of oxygen? 16. These boys are not making this up. They're looking at a periodic table or they've memorized it by now. How many oxygens are there? 6. So what is 16 times 6? 96.0 grams per mole. So then you have to add those values up. What is 72 plus 12 plus 96? 180. C6H12O6 equals 180 grams per mole. That is going to be your conversion. You need to know how to come up with that. That's first semester stuff. So let's do that problem. I have 54.0 grams of C6H12O6. 180 grams of C6H12O6 is going to be equal to 1 mole of C6H12O6. Now, if you were kind of a noob at this, kind of a beginner, I would stop there. But can I add another equation to this? Yeah, what can I add, Emma?
Can you add
The other one, that's right. The combustion. Where would I put the 2808 kilojoules?
At the top.
Yep. Why?
Because the moles would have to cancel out.
And it's 2808 kilojoules per how many moles? 1. Yeah, we'll work that out. Okay. So to go over this, this is your molar mass conversion. And this is your enthalpy heat of combustion for glucose. Right there. So let's solve this. 54 divided by 180 times 2808. This is going to equal 842.4 kilojoules. Now, is that going to be gained or lost? So here's what you can do. You can say 842.4 kilojoules lost, or you can just say negative 842.4 kilojoules. And that negative right there indicates what? It was lost, right? So there's multiple ways to say it. Like if I lost $20, no one says, I lost negative $20. We don't say that. But if I look at my bank account, it's going to say negative $20. And that negative indicates it's gone. So you can say it either way. Yeah, you can say change in enthalpy of combustion equals negative 842. Oop. All right, we finished section 3. We're on great track now. We have 2 days per. We have 2 days for section 4, tomorrow and Monday, and 2 days for section 5, Tuesday and Wednesday. We should be on track for you guys to work on your review on Thursday. See ya.